we do this. So I'm starting the recording. If there's anybody that's got anything against recording, please let me know and I'll stop it right away. And sharing my screen. Okay, I'll share my entire screen. That should be fine. Okay, could anyone tell me if they can see my screen right now? You can? Host to everyone, ready to go. So someone's called host, someone's called 111. This is pretty funny. Can you see my screen? Yep. In that case, I'll switch to this. I could put this full screen. I have tried. The problem is that when someone asks a question and I come back from full screen, my browser shuts down and I have to restart everything and the meeting. So I won't do this. And this is the maximum zoom I can, as you can see, that I can get. So if it's too small for you, please sort it out with your own setup. I cannot do better on this. Okay. So the problem that we're going to be looking at right now is, oh, excellent. I've got notification on top there. Excellent. Let's admit, Gabriela. So the problem that I said that we'll be talking about is B3. Okay, so B3. If there's any problem, if you see that what I'm writing is not in sync with what I'm saying, please let me know as well. I have had some technical difficulties in the past. So B3, the first question is consider the equation, and this equation is x2y double prime plus 4xy prime plus x squared plus 2 times y equals 0. And we're talking specifically about this equation. Oh, this is going to be really annoying. Can I? There's some kind of setup to accept everybody automatically. Enable waiting room. What if I disable waiting room? Let's see. Okay, so that's our equation, and we're particularly interested at the behavior of the solution near a singular point. And that singular point is regular, so near the regular singular point. And this point is x equals 0. So you might remember from last week, from what Stephen has presented, how to find out singular points. You're essentially looking at the zeros of the function that is in front, or the polynomial that is in front of your the highest derivative. And the way to check whether it's regular or irregular, we might have an example of that later, or maybe it's in B4. Let me check. Yeah, I think it's in B4. So maybe I can check. I can cover that at the end as well. Otherwise, I refer you to last week's workshop. So we're interested in this equation around that point. And the first question that we ask you is essentially find the, sorry for this, the indicial equation associated with the Frobenius series solution. Okay, so that's the first question. Sorry, I just kind of feel I'm very uncomfortable to write with this setup with the laptop. Let me just move it around a little bit. Hope that's not going to disturb anything. Okay. So that's the first question. And so you might remember how we write down a solution in terms of the Frobenius series. So this is essentially how we do it. So you might remember writing that the solution y can be written as a series of monomials. So we're going to write down a0 x to a certain power. We'll start off with the power r plus a1 x to the power r plus 1 plus a2 x to the power r plus 2, etc. And well, this is kind of annoying to write,
So we have a little bit of, we'll have a better way to write this, a bit more condensed way to say exactly the same thing. And it's to write it down in terms of a sum. So we're going to be writing down a sum from I equals 0 to infinity. And I being an integer, I use I to denote an integer. So it's going to be AI times X R plus I. And you can see there that I'm covering all my bases because I equals 0 is A0 X to the R, plus then I equals 1, A1 X to the R plus 1, and so on and so forth. So we're covering everything there. And okay, so our equation, the equation that we're looking at, is comprised of y prime, and y double prime. So what we're interested in is expressing these derivatives as a function of these powers of x. So let's go around and let's do the first derivative, y prime. So if I want to do y prime, I'm essentially differentiating all these monomials. So I'm going to have AI, which remains AI, it's just a constant, and I've got x to the power r plus I. So that's going to become r plus I, drops from the exponent, x r plus I minus 1. And that's it. So that's the expression of our first derivative. And then the second derivative is not going to be more complicated. I'm just differentiating this once more, and I get AI r plus I, and now I'm differentiating this bit. So I'm dropping my exponent, which is r plus I minus 1, and then I am taking x to the power r plus I minus 2. And here I've got the expression of all the derivatives that I need to plug in this Frobenius series into my equation. So what we're going to do just now is write down the equation, replace all the terms in the equation by the corresponding Frobenius series. So let me just remind the equation here: x squared y double prime plus 4x y prime plus x squared plus 1. That's y equals 0. Is that correct? Yes, that's the equation. And so what I'm going to do just there is plug in so simply. I'm not doing anything crazy here. I'm just plugging this expression, or these three expressions, this one, and this one. I'm just plugging them in and replacing these three occurrences of y. So the first one is x squared times y double prime. So I'm going to be looking at this term here, and that's going to be giving me a sum for I equals 0 to infinity of AI r plus I minus 1. And then I get x to the r plus I minus 2 times x squared. So that's giving me x r plus I minus 2 plus 2. Then I'm looking at my second term, which is this guy here, 4xy prime. So that gives me some, this time I'm looking at this guy here. So that's giving me the sum from I equals 0 to infinity of, and I need to multiply this by 4x. So it's 4ai r plus I, and I've got x to the r plus I minus 1 times x. So x to the r plus I minus 1 plus 1, so x to the r plus I. And that's it for the second term. And I'm going to take it slowly. That third term here, I'm going to break it down between the x squared times y plus y. So I'm just developing this product, and then I'll apply the formula. So can I get all this on the same page? Yeah. So the first term is x squared times y. So I'm going to be writing down, I'm going to be looking now this time at this guy, right? I equals 0 to infinity, and I'll have to multiply this by x squared. So ai x to the r plus I plus 2. Okay. I'm multiplying it. I'm multiplying it by x squared. So I need to add 2 to the exponent. And the last term is where's my equation? The last term is just y. So plus sum of I equals 0 to infinity of AI x r plus I. And that long expression has to be equal to 0. Okay? Now there's a trick from that moment. And the trick is that when we get an expression like this, what we actually care about is looking at comparing the coefficients in front of monomials of the same degree, right? So what we're looking at here is I've got x to the r plus I here. I've got x to the r plus I there. I think I see a lag in my screen display. There you go. I see x to the r plus I there. But here I've got x to the r plus I plus 2. So there's a difference. But I can actually, change a variable in there, in that specific term where I put the arrow, so that I get x to the r plus I instead of x to the r plus I plus 2. And the way I do this is just very simply by resetting the counter on I. So instead of writing, I'll change color to explain that. Instead of writing that sum from I equals 0 to infinity, in fact, here you can see that stuff starts at 2 and goes to infinity, right? So instead of starting from 0 to infinity, I can just say I equals 2 to infinity, okay? And I'm going to have x to the r plus I, corresponding to the same term that I wrote in black. But now I need to be careful about the a sub I here, because remember the a sub I, the I there, the index there, started at 0. And so now if my counter starts at 2, I need to subtract 2 from it, okay? So that's going to be I've just kind of made a mess there, I minus 2, okay? So I can just, by changing that variable, that I, by resetting this counter, I'm going to infinity, so that series is infinite. So I can just, by resetting this, convert my expression from x to the r plus I plus 2 to x to the r plus I. And that means that I need to be careful about like the index that is coming with the AI, and I need to turn it into a I minus 2 so that the first term in that series is still a 0. Okay, does that make sense? If you have any questions, please let me know. Please interrupt me. I would like to be interrupted if there's something that isn't clear. And so if I continue writing my expressions, the equation, by replacing the terms that were the term that was that had the wrong exponent by this better version, then I'm getting this expression: I equals 0 to infinity AI r plus I minus 1 x r plus I. I can actually factorize everything. That would be nicer, but I'll just do this in this fashion so that you can see the next step in the reasoning more clearly. X r plus I. Now I need to be careful. This is a sum from I equals 2 to infinity of a I minus 2, sorry, x r plus I, it's an x here. And my last term is sum I equals 0 to infinity of a I x r plus I, and that's equal to 0. So that's the expression that I get at this stage. Again, as you might remember, what I was saying is that we're interested in comparing each the powers, similar powers for these monomials, right? The x to the r plus I. So we're going to be looking at the initial stages where I equals 0, which is going to be corresponding to x to the r. Then we're going to be looking at x to the r plus 1, x to the r plus 2, x to the r plus 3, and potentially get a recurrence coming out of it. So what we can see here is we can see 3 terms starting from I equals 0. Okay, so these 3 guys. And the 4th term, unfortunately, starts from I equals 2. When in fact, unfortunately or fortunately, depends on how you want to see this. So what happens here is what you will get out of this is that only from I equals 2 these four terms come into play. So we're going to have to write I equals 0 and I equals 1 separate. And then we can write a relationship for any index beyond that. So let's do this. So how about we write it for I equals 0. So for I equals 0, remember this is x to the r. The equation that we get is a0. I'm just looking at the first term at the moment. R plus 0, so that's r. R plus 0 minus 1, so that's r minus 1. That's the first term. Then the second term also has an I equals 0. I'm looking here. So that's going to be 4i0, r plus 0, so that's r. That third term here in red does not have any x to the r term. I equals 0 is not comprised in this infinite sum. And the last term here gives me a0 x to the r as usual, right? And that's got to be equal to 0. So that's our first equation that comes out of this infinite series equation. The second one is I equals 1, so that's going to be looking at the coefficients in front of the monomial x to the r plus 1. And what we get here is, again, I'm just looking at the first term, and I get a1 times r plus 1 times r plus 1 minus 1, so that times r. The second term gives me 4a1, r plus 1. Third term again doesn't have I equals 1. And then the fourth term gives me a1, and that's just it, a1. And that's got to be equal to 0. Okay? So that's our that's our second equation. And then, as I said, the four terms can be put together. So we have I greater or equal to 2. That's going to be x to the r plus I. And the terms that are going to be proportional to these monomials are what's left in there. So that's going to be ai r plus I, r plus I minus 1 plus 4ai r plus I plus, now this time we add the third term, which becomes important now. But you can see it comes in with an I minus 2, and I starts at 2 here. So that first term is going to be involving a 0. And the last term is ai equals 0. And we get that, that relation. So that's for I greater than 2. So what we get out of this calculation, out of plugging that Frobenius series into our equation, is this set of three equations. Now, if you look at the first equation, the first of these equations, which is this one, okay, what you get is the following. So I'll call this equation 1. So if you look at 1, what you get is a0r r minus 1 plus 4a0r plus a0 equals 0. That's completely undetermined for a0. So I can just, all I know is that a0, you know, either a0 is 0, but that might not lead to an interesting solution, or a0 non-zero. I can just take it out of the equation, and I get r minus 1 plus 4r plus 1 equals 0, which, did I miss I missed a term somewhere, didn't I? I've just seen in the solution a 2 coming in somewhere. Oh, it's why it's oh, okay, it's not a 1 here, it's a 2 in this. So if you go back to the original equation, that was a 2 here, that was not a 1. Okay, so let me just see if I, no, I had it right in the beginning. I just miscopied the equation when I wrote this down here. Okay, so pay attention to the equation. There was a 2 there, and therefore, if you go back to the equation when I plugged in the Frobenius series, there's a 2 that comes in here. Okay, and there is also another 2 that is coming here. Hope you can see what I'm doing. And the last term of each of these equations, which is just a0, a1, ai, also has a 2 in front of it, like here, there, and there. Okay, everybody follows? Is there any issues there? Let me just briefly check the chat because I'm just feeling very lonely suddenly. Okay, no questions so far. Does that make sense? Are we good there? So there's a 2 that comes in here, and there's a 2 that comes in here as well. Okay. So if I continue this calculation, I can develop this and get that it's r squared plus 3r plus 2. And there I immediately see a root of this, which is -1. So it's going to be r plus 1 times something, and that something it's got to be 2, so it's r minus 2, like this. Okay. And so what we get here is 2 solutions for this equation. We get it's plus 2. So we get, no, it's minus 2 actually, sorry. R squared, then 3r, then I get plus 2, then that's r squared, plus 2. What am I writing? So it's plus 2. So what we get here is 2 solutions. We get either r equals -1 or r equals -2. Okay, we have 2 solutions here. And so, and that's, sorry, that was the indicial equation. The question that was written here was to give the indicial equation, and the indicial equation is this equation here. Okay, so that is the indicial equation. It tells you what the what Frobenius series you can write based on the value of r. Here we have 2 choices. We have r equals -1 and r equals -2. Okay, so the next step in this problem. Is there any questions so far? It's very silent. I hear nothing. There's no comment whatsoever. Are we all good here? Are there any questions? Thank you, whoever wrote OT. Is that all right? Should I continue? Okay, so then the next step was consider the Frobenius series. So the question was consider the Frobenius series y equals x to the -1 sum from I. Oh, this is an n now. Let's change my indices. I'll continue with I just for the sake of it. I equals 0 to infinity of ai x to the I. And a0 different from 0, and find the recursion relation, and then the solution. Okay, so what that means here is that if we rewrite the expression that we get, that we're given in the text of the question, we're getting sum from I equals 0 to infinity of ai x I minus 1, right? Now, if we look at the expression of our Frobenius series that we implemented in the first part of the question, which is this guy here. I don't have any colors left to express myself, so I'll put an arrow on the other side. What we had was just a sum, okay, from ai r plus I to the x to the power r plus I. So if we compare it with what we have here, what we're given in the question, what we can identify immediately is that we're considering r equals -1. Okay. Comparing this to our Frobenius series, we identify that we are working with r equals -1. Okay, so, well, very good. So now we can get going with r equals -1. So r equals -1, again, remember the set of three equations that I wrote down. This is what we're going to be working with. So it's going to be a bit tedious for me to move from one screen to another. So I'll try to have a look at it here. So what we have here, the first line, the first equation, we already dealt with it. That first line gave us the initial equation. No need to use that further. So there's equation 2 and equation 3 that we need to work with. Let's have a look at what equation 2 gives us. So equation 2, if I replace r by -1, that term is 0, right? That term is 0 as well. And so what we're left with is 2a1 equals 0. So a1 equals 0. That's as simple as that. So a1 equals 0. So a0 is always undetermined. Remember that we're looking at linear differential equations. Therefore, the solution is up to a constant, it's a multiplicative constant. So a0 will remain undetermined at this point. So now the question is, what does equation 3 gives me? And so I need to copy this equation. Do I have it somewhere here where I can actually copy it? So that's ai times r plus I minus 1 plus 4ai r plus I plus ai minus 2 plus 2ai equals 0. I'm replacing now r by -1. So that gives me ai I minus 1, I minus 2, or by -1 exactly, plus 4ai, I minus 1, plus ai minus 2, plus 2ai equals 0. I can factorize some of that. So I can say that it's ai factor of I minus 1, I minus 2 plus 4, so I plus 2. And then I've got a term here, which is plus 2. And I'm going to say that this is equal to minus ai minus 2. And looking at this, this inside the parentheses, maybe I can actually simplify this a little bit more and say that this is the I squared plus I minus 2 plus 2. That's very nice. That simplifies very nicely. And so what I get here is ai times I plus 1 equals minus ai minus 2. Okay. And I believe I've just got the recurrence relation that we were looking for, which is this recurrence relationship there. So what I've just done, it's all at this point, as you see, the whole work, in a sense, is relatively straightforward. We start off by saying that we have a Frobenius series. We write down that Frobenius series, which is I'll just take down, take another color, which is this equation there. That's our ansatz. It's our Frobenius series. Then we know that we're dealing with a linear equation which makes derivatives of this function appear. So we calculate these derivatives in the same manner. We plug that in the equation. Remember these little tricks here when we plug it in. Trick number 1 was writing down everything in terms of series like this, identifying the fact that this guy has not the same, doesn't have the same power, resetting the indices, and then what we are doing is very simply here matching the terms and identifying what happens for I equals 0, I equals 1, and whenever we can, as early as we can, we write that sort of indicial relationship here. Once we've got this, the first equation gives you the indicial equation that tells you what the value of r is. That's equation 1, which we've just done here. And then you just unroll the rest of the calculation. The second equation gives you the first term. Turns out we have a second equation here, so we're lucky or unlucky, depending on how you see it. So the second equation gives you A1, and then the third equation will give you A2, A3, A4, etc. So we get to that indicial equation here, or sorry, index equation, I don't know how to call it, where it's no longer a specific AI that you're looking at, but it's AI for I greater than a certain value. And that gives you anything else that you want. Particularly, that gives you this recursion relation. Okay? So all we have to do now is find the solution to this Frobenius series problem. But we've got these relationships there. So, so it's actually not going to be too complicated at this point. What we need to realize first is, let me try and use this. What we need to realize first is that this recursion relation ties AI with AI minus 2. Okay? And so because it ties AI with AI minus 2, it ties all the odd indices with themselves, and it ties all the even indices with themselves. Okay? Another thing that we notice here is that, well, A0 is whatever A0 is, but we have A1 equals 0, right? And because A1 equals 0, and AI, I plus 1 equals minus AI minus 2, and not AI minus 1 or AI minus an odd number, then we know that the AI are equal to 0 for all I odd. Okay? So we only care about the even I. Okay, so A0, A2, A4, etc. So what we can notice here is AI equals this. So maybe we can look at what A0 was equal to A0. I'm just writing a triviality. It's ugly to write it like this, but it just helps sort out our thoughts. Let's have a look at what A2 is equal to. A2 is minus A0 over, and if I take I equals 2, I'm looking at this expression up there. I get 2 times 3. Okay. And if I look at A4, A4 is going to be minus A2 divided by 4 times 5. Okay. So again, if I reset this in terms of A0, what I get is the minus simplified. So I get A0 and I get 2 times 3 times 4 times 5. And you can keep going with that. So what you see there, in fact, is that this is going to be minus A0 over 3 factorial. This is going to be A0 over 5 factorial. So AI is actually equal to, sorry, it's going to be the even, you need to be thinking about this carefully. It's only even I, so I'm going to reset this for 2I, right? To only cover the even i's. And it's going to be equal to, remember this alternating minus sign, so this minus 1 to a certain power. When I equals 0, we're here. So when I equals 0, we're getting plus. So to the power I. When I equals 1, we have A2 here. There's a minus sign. That's fine, and so on and so forth. And then what we get is a 0 here divided by, and in the numerator here we have the index that we have on the left. Take, for instance, here, this is 4. Now on the right hand side we have 5. So that's index plus 1. So the index here being 2i, we get 2i plus 1 factorial. Okay? And you can keep checking that if you want. So this is a good way to spot that that recurrence relationship to spot that relationship in a recurrence kind of way. Okay, so now that we have this, we can just write down the final solution. And our solution, which I'll call y1, is, let's remember what we had. It's a0 and it's x to the minus 1. We started the series at x to the minus 1. Then we have a2, that is going to be x1, a4, that's x3, a6, x5, etc. Right? And so, well, as usual, we can factorize everything by a0. So that's a0, and also we can also factorize everything by x to the minus 1, because this x to the minus 1 is going to bother us in the expression. And we get 1 plus a2 divided by x0. So remember, a2 was a0 to 3. Okay, sorry, there's a minus sign here. a2 is there. So that's minus a0 over 3 factorial. So that's minus 1 over 3 factorial. We get an x squared here. Then we get plus a4, which is a0 divided by 5 factorial times ax to the 4. Then we're going to have a minus sign. Remember this alternating minus sign that comes in. That's going to be 1 over 7 factorial x to the 6, etc. And that's what we get here when we write down this this expansion. Something that we can do to make this look a little bit better, because we kind of see a pattern there, right? We kind of see something that looks like a Taylor series around 0. We see only odd powers like this, or only every second power is used. We see there's an alternating minus sign that comes in. We can also see 1 over a factorial that corresponds to the index. So maybe something that is interesting would be to actually multiply all this thing on the right-hand side by x. So let's do this and see what we get. a0 x to the minus 2. And that makes an x come in here. And then we get minus 1 over 3 factorial x3 plus 1 over 5 factorial x to the 5 minus 1 over 7 factorial x to the 7, etc. Okay? And there we see something that should be immediate, that should just immediately spring to your mind. This is a sign. So what we get here is a0 x to the minus 2 sine x. This is the Taylor expansion of the sign in the vicinity of 0. Okay? So this is what we get here. Are there any questions? That's the solution of this part of the question, y1. A very, very nice solution to a complicated equation, but found relatively simply, with long calculation certainly, but relatively simply, without any major difficulty using Frobenius series. Are there any questions? Yes, no, silence? Have you had your coffee yet? Okay, Hannah seems happy. By any means, do ask questions, do interrupt me. We've got like about 10 minutes left. Excellent, good. So I'll try and go quickly over the end. What do we have? Use reduction of order. Yeah, we haven't done that. And then, oh, that's tight. Okay, I'll try and cover that. And I'll just give you one piece of advice for before. So the next question is use reduction of order to find a second solution. Okay, so reduction of order, when you read this, when you have one solution to an ODE and you need a second one, you know that's got to be something related to the Wronskian. So what you need to look at is here, what can we do with the Wronskian? And then there's one formula that you should remember. Remember if you write down the equation as y double prime plus p y prime plus q y equals 0, you can express p and q, CF, the first 2 weeks of workshop. And in particular, what we know is that this polynomial p is equal to minus w prime over w, w being the Wronskian. And p in the equation that we have, so let me just, where is the equation? The equation is x squared y double prime plus 4xy prime plus x squared plus 2y equals 0. That's our equation. So p is 4x divided by x squared. So simple. So what we have here is w prime divided by w equals minus, I'm just putting the minus in there, 4x divided by x prime. So I can just, point is minus 4 over x. Apologies, I should have simplified this. The point is just to solve this equation to end up with the Wronskian. So solving this, left-hand side, integrating, we get the log of w, and on the right-hand side, we get minus 4 log of x. It's a natural log. And so I write natural log ln so that it's not ambiguous. For log log, I typically assume that we're talking about the log 10, just differentiating them to overemphasize this. And therefore, what we get here is that w, the Wronskian, is x to the minus 4. Okay, taking the exponential of this. Exponential of something log x is x to the power of something. And then there's some formulas that are quite interesting, particularly if you remember the definition of the Wronskian. The Wronskian, if I've got two functions, is y1, y2 prime. It's a determinant of the functions in their derivatives. Minus y2, y1 prime, and that's our Wronskian. Something that we can identify here, we know y1, we try to find y2, so we can divide everything by y1. So that gives us y1, y2 prime, so 1 here, minus y2, y1 prime divided by y1 squared, and that's w divided by y1 squared. Did I hear something? Is someone asking something? 1 hour of not hearing anything makes me hear ghosts. Cool. Are you still, I think my camera's frozen. Are you still capable of hearing me? Oh, good, excellent. Okay, so I'll disregard the frozen camera because I'm definitely not looking in that direction right now. Okay, so that's what we get. And what we notice here on the left-hand side of this equation is a canonical derivative. It's very simply y2 divided by y1 prime, right? Remember this vu prime minus uv prime divided v squared. That's essentially what we get on the left-hand side. And on the right, we get w divided by y1 squared. Excellent. That is giving us a lot of information, because then if we invert this operation of the derivative, then what we get is y2 divided by y1 equals the integral of w divided by y1 squared dx, or in other words, what we get is y2, that second function entirely expressed as a function of the first one, in this fashion. Okay, so that's the formula that we're going to be working with. So now we plug in very simply in that formula. And again, you know, one thing that I like to emphasize to students is that, well, sure, you can learn this formula by heart. You can learn it. But why? It's so simple to remember, because you have to remember the Wronskian's formula, right? So that you know, derivation that I've just done takes 10 seconds. So why bother learning that formula that I gave you on the bottom right if you can simply find it in 10 seconds? And at the same time, finding it in 10 seconds reactivates all your calculus skills, right? So I don't think learning this by heart is necessary. Anyway, so what we're going to do there is plug in the functions that we have. So remember, y1 is a0 x minus 2 sine x, and the Wronskian is x to the minus 4. Okay, let's see what that gives. So y2 equals, so y1, so we get a0 x minus 2 sine x times w, which is x to the minus 4 x0 squared, a0 squared, and x to the minus 4. Sorry, I'm just lost in sine squared x there. And that's dx. Okay, so simplifying this, we get x minus 2 sine x divided by a0. And here we get 1 over sine squared x dx. Okay, so that's actually a very simple, well, it's not very simple, absolutely not simple, but it's a typical integral that you see again many times, and I'm not sure I've got a lot of time to prove it, but here, if you want to understand this, you just have to change variable and write z is tan x. And you might remember that the derivative of tan can be expressed as 1 minus blah blah, or 1 over cos squared. And it's nice to have a cos squared because we have a sine squared here, right? So we can write down that dz is 1 over cos squared x dx. Okay. And so if I plug that in, what I'm getting is that y2 is x minus 2 sine x divided by a0 integral, and what I get here is replacing the dx by cos squared x dz. I get cos squared x divided by sine squared x. Quite nice, right? Dz. So I'm getting, this is nothing else than 1 over tan x squared, but tan x squared is z, so this is 1 over z squared, right? So what I'm actually looking at here is y2 equals x to the minus 2 sine x divided by a0 times the integral over 1 over z squared dz, nothing else, not that complicated. So ultimately what you get there is x minus 2 sine x over a0, and then here you get 1 over minus 1 over z, sorry, the integral of 1 over z squared, and z is tan x. So the answer is x minus 2 sine x, there's a minus sign that comes in front of it, over a0 tan x, and tan x is sine over cos. So a million simplifications later, we end up finding that y2 is minus x minus 2 divided by a0 cos x. And that's our solution. Okay. So again, I mean, it's up to a constant, so you can just take the a0 out of there, or or put the b0 instead of having 1 over a0 to simplify the writing. But that's essentially what we get. And since it's 55 past now, I don't know if you've got anything after this workshop. I do have a meeting. I'm gonna just fly over the last question and give you one piece of advice for before. Do write down your questions if you have any questions. I do not hear anything, so I find it a bit strange. Something happened. Good so far. Okay. So very quickly, if you plug in, the question is to plug x minus 2 equals z of x, right? You see this x minus 2 is there, right? So if you plug in x minus 2 times z, oh, and by the way, the x minus 2 was already in the in y1. Where's my y1 here? Yeah, there it is. The x minus 2 was already in y1. So this is the format of the solutions to this equation, right? It's always that. Coefficient times x to the minus 2 times a trigonometric function. So if you plug this into the equation, there's many ways to do it, but it's just polynomial, so it's very simple to write down y prime, y double prime equals, plug it into the equation. And then you will end up finding an equation for z, which is z double prime plus z equals 0, right? And that's a typical Helmholtz problem, just dropping the name in case you're interested, which admits the very simple trigonometric functions as solution. So this is what you would end up with, okay? The last thing that I want to touch upon is regarding B4. Now what happens in B4 is if I go back to my indicial equation, which should be here, right? So if I go back to my indicial equation, which is here, in B4, what happens is that you get imaginary solutions to the equation. So you get r equals I and minus I as solutions. I not being the index, I being this time the imaginary number. That was actually, I should have not used I in this workshop. I apologize for this. So since R is imaginary, when you plug it back into your equation, you might be a bit confused, but it's no problem. Just plug R equals I in your equation, develop the calculation, and what you'll end up with is essentially just a complex series, right? In particular, do remember for B4, do remember that you'll have R to the I, okay? And R to the I, you can write it as E to the I log of R. So if you want to split the real and the imaginary parts of this, then you write down that this is cos of log of R plus I sine of log of R. And you get here the real part, and this is the imaginary part. So that's just a little trick there is to it. And you end up with this Frobenius series, which is complex. And then we ask you, can you give us two independent real solutions of this equation? The answer is yes. Take the real part of that Frobenius series, this is one solution, and take the imaginary part of that Frobenius series, that's your imaginary, that's your second solution. And then the rest of B4, actually, if I look at it, the rest of B4 is pretty similar in content, in technique, as B3. There's just the added question of showing that x equals 0 is a regular singular point, but you've covered that already last week with Stephen. So there's no need to spend more time on that, I think. Okay, are there any questions? That's going to be finishing this workshop. Is there any questions? What does it mean in the assessment question by truncates to a polynomial? I don't have the assessment question in front of me. I'm sorry. I would need to log back to Minerva. To Minerva. Truncates to a polynomial. Oh, I see actually what you mean. Okay, I see what you mean, Luke. What we write down here. My goodness, this camera is really strange. What you write down here is Frobenius series. Frobenius series are an infinite. Is an infinite series, right? It is a polynomial technically, but I think that in the question, what they mean by polynomial is a finite series, right? Polynomials means poly is multiple, nomial is a monome, right? It's the power of x, right? Times the coefficient. Polynomial means multiple of them, right? You add them right together. So when you have a series, you have polynomials, right? But it's an infinite series, and I think in this context, truncates to a polynomial means truncates to a series of a finite number of terms. So in that case, can you show me that AI equals 0 for any I greater than a certain index? That's what it means, I think. Does that answer your question, Luke? Cool. Anything else? Thank you. I hope that I can see you in person next week. All right, thank you, bye.